We are the USASOC Quiet Drone Team. Our team worked in collaboration with the U.S. Army Special Operations Command to design a drone with a reduced acoustic signature compared to an ordinary drone design. Our drone had to be flown by a single operator in low altitudes, while also not exceeding dimensions of 40 inches by 40 inches. It was found through extensive research that a typical quadcopter drone design emits noise levels of 70 to 80 decibels. We found that most of the noise generated by a drone comes from the tip of the propellers. The tip speed of a propeller has a direct correlation to the drone's acoustic signature. Here are the equations we utilized for our modeling. We used this thrust equation to find the angular velocity of the propellers, which was then used to calculate propeller tip speed, followed by sound power, which was then converted to sound power level. Here we have two graphs representing the results from our equation modeling using the equations previously mentioned. For the first graph, the angular velocities were found for propeller diameters ranging from 6 to 16 inches. These values were then used to calculate propeller tip speed, followed by sound power and sound power level, which is measured in decibels. As diameter increases, the sound power level decreases. For the second graph, propellers of diameters 12, 14, and 16 inches with blade counts ranging from 2 to 5 blades were used to calculate their respective sound power levels. As the number of blades on each prop increases, sound power level decreases and seems to level out at around 5 blades. Here are the photos of the soundproof testing room and testing apparatus that we utilized to isolate the propellers and motors from the drone. The testing apparatus was used with the microphone setup to take data points of an individual propeller to find the relationship between thrust, RPM, and sound produced. Here are our results from testing. The first graph was created by modeling the three quietest propellers on the market via our equation calculators to obtain the sound power levels in decibels, while the propellers were generating thrust values between 200 and 400 grams. This graph shows the data of three 13-inch three-blade propellers. The second graph was created utilizing our testing apparatus to isolate the three propellers mentioned. It can be seen that the higher pitch 13 by 12 propeller was the quietest. After analyzing the testing results, we decided to use 13 by 12 three-blade propellers. All other parts were ordered to support this decision. Our design uses a lightweight frame and reliable motors. The final testing was conducted in the same testing room. The Typhoon Unique drone and our final drone design were both tested at hovering speeds using the same microphone and program mentioned in the testing setup slide. The Unique drone, which is one of the quieter drones on the market, tested at 75.4 decibels, while our drone tested at 64.7 decibels, which is a significant reduction. This concludes our presentation.